3 students, welcome back to Physics channel with me, Pratama. Today, I want to talk about an object that is rotating around a central mass, and in this case, I'm going to refer to the Moon and to our Earth, where the Earth is the central mass and the Moon, of course, is rotating around the Earth. So, the Moon is in essence simply a satellite, and as you can see, it's following a circular path. And here, we have a circular path, and the circular path is due to the fact that this object is moving with a particular velocity and is always experiencing a force that is at right angles to the direction that it's moving. And here is the velocity. You can see it's always moving at a tangent to the circle, but it's always experiencing a force. And that, of course, is the centripetal force, and as a typical force, is a force that causes it to change direction. In other words, the forces always apply inwards to the circle and is at right angles to the velocity at any given moment. And of course, in this case, the centripetal force is provided by gravity. And so what we have here is a factor that shows us the gravity pulling in towards the Earth. And of course, also you see two arrows because, as you should know from the law of gravitation, that gravity is actually a mutual force of attraction between two objects. And in this case, it is the Moon and the Earth itself. And so therefore, the Moon is exerting a force on the Earth, and the Earth is exerting a force on the Moon. As a result of this force, the object is moving in circular path because the centripetal force is equal to the gravitational force. Now, if I somehow have a superpower to turn off the gravity, let's see what happens. Well, you can see it just goes off at the tangent. In fact, Newton's first law takes place. Now, let's have a look at the mathematics of this situation and show how we can determine the orbital velocity of any given satellite at a certain distance away from a central body. So, here is our example again of Earth and the Moon. And of course, it is going around in a circle. And that's simply because that the angle between the factor that represents the velocity is at right angles to the actual force that exerts. And of course, it's the gravitational force that actually is the centripetal force. So, let's have a look at the mathematical expressions of this phenomenon. The first thing is to understand that the force due to gravity is equal to the force due to the centripetal force. And that's how we write it. F at the subscript of G is equal to F subscript C. You should know also that the gravitational force is determined by a number of factors. It's determined by both masses and the distance between them squared. And Newton's law of gravitation states that the gravitational force is equal to G times m1 times m2 over r squared. And of course, our r here in this case is the radius right here, and it's always measured from the center of mass, which is the m1 and m2. And of course, that G is the gravity constant, which is always 6.67 times 10 to the power of negative 11. And then the centripetal force is equal to mv squared over r, which we have studied in our previous chapter. Again, r is of course the same. That is the radius between our two masses, which is the Earth and the Moon. Then, the v here is orbital velocity, which we are looking for. If we rearrange this, then we can see that we'll end up that this mass over here, the small m, is actually the moon. And so what happens is the mass can be cancelled out. Over here, leaving you the only mass in the whole equations as the central body mass. Here is the mass of the Earth. And so, if we rearrange it, that we will get V squared is equal to Gm over R. The first thing that we need to understand here, that this V represents the orbital velocity, that is the velocity at which the satellite is moving. In this case, the moon is moving in orbit. Secondly, you'll see that within the other side of the equations that we have two values that are constant, which is the capital G and capital M. In other words, the gravitational constant multiplied by the mass of the central body will contribute to this orbital velocity. But if I want to change the radius of my satellite, yes, the orbital velocity will change. But the fact is that the mass of my moon has no bearing on it. You'll notice that there is no mass of the moon needed in this equation. So let's say if I suddenly were to remove the moon and replace it with a 1 gram pebble at this radius, then it will have exactly the same orbital velocity as if I have the moon too. Now we know here that the mass of the moon is independent. It is not involved in this equation. Okay guys, that is how to derive the formula of orbital velocity. I do hope you understand about the derivations of the formula and can take notes from this video. We will meet again and discuss about the example of the question in our Zoom session and also WhatsApp group. Thank you for your attention and bye-bye!